Okay, here's an example which will be like the one on the quiz 6b, and it shows that it's possible to recapture a closed form formula for a sub n from the generating function. Closed form means in this case that it'll have a variable n that will allow you to figure out what a sub n is using the formula, and it won't have any summation n equals 0 to infinity in it, or ... with a plus. So here's the example. Let a sub n be the number of multi-permutations. So these are like pin numbers or anagrams. Length n from the multi-subset. This time I'm going to let there be p's, q's, and r's. So they're similar to the 1s, 2s, and 3s, but a little different. Just p's, q's, and r's. There's as many p's as you want. There's only one q, and there's as many r's as you want. But here's some more requirements. There's always going to be one q in every single one of your pin numbers or multi-permutations of length n. In fact, that means that since there's only one q and there's always one q, that means that we can only have exactly one q. So that's a little redundant, but I just wanted to show different ways of writing it. And an even number of r's. So you can't have an odd number of r's in your multi-permutation or sort of pin number with p, q, and r. Now 0 is even, so you can have 0, 2, 4, 6, 8, and so on. Now we have to see some examples of these. So in this case, n equals 0, there's none. The reason for that is that you have to have at least one q. So if you don't have any letters at all, you can't have a q, so it's illegal. If you didn't mention that, then you could say that there is an empty pin number. But in this example, there's no such thing as an empty pin number because they always have to have at least one q. Which brings us to n equals 1, and there's only one option because it has to be q, because there has to be at least one q, and no more than one q. So a sub 1 is equal to 1. For n equal 2, you've got to have a q again, and that limits the other one to p because you can't have just one r. You have to have an even number of r's. So you have pq or qp, so a sub 2 is equal to 2. For n is equal to 3, now we've got some options. So you have to have a q, and then you could fill in the rest of it with p's, the first three, qpp, pqp, ppq, because that would be 0 r's, which is an even number of r's, so they're okay. The other possibility is 2 r's, because that's only there's no room for 4 r's, and you can't have just one r. You have to have an even number of r's. So you have QRR, RQR, or RRQ. So that's a total of 6. So 1, 2, 6, 0, 1, 2, 6. Not seeing a pattern yet myself. But actually, you could probably come up with a pattern for these. Let's see what the generating functions tell us. All right, here's the generating function. So we have P, Q, and R are the three symbols that are going to be made into an ordered list or multi-permutation. And so we need 3 factors in g of x. And they'll just do them in that order for P, for Q, and for R. So for P, we're allowed to have any number of P's given n up to potentially any number of p's at all. So that means we need the whole sequence 1 plus x squared over 2 factorial, all the powers of x, with the same factorial underneath to take care of the duplicates. Then for q, it turned out that there was only one q, and there has to be one q in each of them. So that means it's a very simple factor, just x, because that has the power 1. No, not even a 1, because that would have the power 0. X has the power 1. And then for r, it had to be an even number. So just to writing it down, what we what we see as the even numbered powers. So x to the 0 is 1, so we have to keep that. Then x squared over 2 factorial, x to the 4 over 4 factorial, x to the 6 over 6 factorial, and so on. And that has a nice trick. There's a nice trick for writing that as an actual function. First one is e to the x again. Then the second factor is x, and then the third factor turns out to be 1/2 times e to the x plus e to the negative x. Writing those out, you can just check to make sure that it works. If you do e to the negative x, it's the same sequence or same series, 1 plus x squared over 2 factorial, and so on. 1 plus x squared over 2 factorial, except that all of the odd powers will have a -1 on top multiplied on them. So it'll actually be 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, and so on. And so when you add that together with the regular e to the x, you should try it, all the odd terms cancel. But you're left with 2 of the even terms for every single power, every even power. So you have to multiply it by 1/2. Which you also might recognize as being hyperbolic cosine, cosh. But there's not really any reason to call it that. It's just nice to know. 1/2 e to the x plus e to the negative x. Because I really want to just multiply this out. So I multiply the e to the x and the x through the parentheses there. And I get e to the 2x from the first term and there. And then I get e to the x times e to the negative x, which cancel. Then I just get left with 1/2 x in the second term. All right, either of those last two lines is a perfectly good answer for the exponential generating function. But now I'd like to actually try to recapture a closed formula. So what I do is, after simplifying as much as possible, I replace any functions like e here with its Maclaurin series. In order to do this, you have to be able to find a Maclaurin series to plug in for some of these functions, so it's not always possible. But for e to the 2x, that's not hard. It's 2x parentheses to the n over n factorial. That's e to the 2x. I have to keep that 1/2 x. Now I can multiply the x into the summation and get x to the n plus 1. And then I can re-index. So here I'm re-indexing to turn all of the n's into n minus 1's. That happened to the 2 to the n minus 1 in the denominator, n minus 1 factorial. And in the numerator, n minus 1 plus 1. And that's a mistake. Underneath the sigma should be n equals 1 to infinity. I'll fix that on the paper. I was seeing the future there because the next step is to multiply on top and bottom of the fraction by n. The reason for that is because we really want n factorial underneath to match x to the n on top. It had n minus 1 factorial. We need to make it match. And so I need to multiply by the same thing on top and bottom. But at that point, it is okay to have n equals 0 to infinity because the first term would be 0 anyways. Well, 0 over 0, I suppose. But I'm going to turn that into n factorial, which is defined at 0 to be 1. So then simplifying, I get n factorial underneath, and on top I have n times 2 to the n minus 1. Now it looks exactly like the definition of the exponential generating function. And so the stuff in parentheses is a sub n. I have to make sure to keep that 1/2 on the outside. And then I also have to make sure that I don't forget the little 1/2 x that's added on. That's 1/2 x to the 1 over 1 factorial. So the final result, a sub n is equal to a piecewise function. It's either 1/2 n times 2 to the n minus 1 for all the powers that are not equal to 1, Or it's that same thing, 1/2 n times 2 to the n minus 1, plus 1/2, when the power is equal to 1, when n is equal to 1. That's because of that last term added on. I have to make sure that I collect its coefficient as well. It'll have a like term of 1. And then I can simplify. Combine the powers of 2 to get n times 2 to the n minus 2. And for that second one, the second piece of the piecewise function, I went ahead and plugged in n equals 1 so that I can see what it is. And when I did that, I get 1/2 plus 1/2 equals 1. So that's the final formula. It's piecewise. It has n times 2 to the n minus 2 and 1. And you can check for several of the values of n since we worked them out above. And for 3, for instance, if you plug in 3, it's not equal to 1, so you use 3 times 2 to the 3 minus 2, which gives me 6, which is what I expected.